Weber is here. Thank you very much, John. So it's my pleasure to introduce Bill Weber, who's here from the University of Trento in Italy, to talk to us about the LISA detectors, which are just an incredible feat of technology themselves. He is an associate professor in the experimental and gravitational physics group in Trento, as I mentioned, and has had a role both, I think, in the LISA Pathfinder, if I'm not mistaken, and also a very important role in this current LISA mission. And so, William, if you want to share your screen and take it away. Thanks so much for being here.
Okay, thank you, Daryl. Let's see, I'll try to share my screen.
Looks great.
Okay, you're able to see something which looks like appropriate slides for the meeting?
It does. It looks exactly on topic.
Okay. So thanks and good afternoon, or I guess good morning to everybody. My name is Bill Weber and I am from the University of Trento, but I grew up, I guess, down the coast from you in Western Canada. I grew up in Los Angeles. I'll start with just a comment on the previous talk. Kelly's presentation was spectacular, and if I weren't already working on LISA, I think I would go and sign up. As someone who's working on the instrument side, after hearing her talk, I really hope we can make things work. And I also hope that my talk, let's say, doesn't scare you away too much. I also hope some of it makes sense. If it doesn't, though, I think the first video that Kelly started to show, which was of the LISA spacecraft aligning and exchanging laser beams, I think this is on YouTube and it's from AEI, and it's definitely maybe illustrates better than I can how LISA really works. But I will try to give an introduction to how LISA works, the measurement concept and the main limiting factors. So what have we already tested, which are free-falling test masses, which are tracked by with local interferometric tracking. This was LISA Pathfinder experiment. And what are we working on today, which is really implementing this long arm interferometry, where we're exchanging laser beams between spacecraft, which are a couple million kilometers apart. And also, I won't talk about this, but the other big challenge, this will be talked about, I think, in tomorrow's presentations on the idea of doing gravitational wave data analysis in signal dominated data. So LISA, we're aiming for a 2035 launch. The official observation window is between 1/10 of a millihertz and something like 1 hertz. We have a 4-year nominal mission. We're working to make it such that LISA can actually work for 10 years, but we're trying to guarantee 4. We're also studying the performance in the extended bandwidth, which goes down to 20 microhertz, so periods of something like half a day. So we detect gravitational waves by the tidal deformation that they make on a constellation of free-falling test masses. So if I can borrow an analogy from our consortium lead, Martin Hewitson, the antenna in LISA is a constellation of free-falling test masses. These are sort of the charges which move in response to the field that we're trying to detect. Our receiver, or the analogy to the radio receiver, is the laser interferometry technique. So at the low frequencies, the sensitivity in LISA is limited by what we call spurious antenna noise. So stray forces accelerating our free-falling test masses, which is in direct competition with the tidal forces, so the tidal deformation that a gravitational wave induces on this constellation of free-falling test masses, which aren't exactly free-falling, and that's the limiting factor. Any stray force is competing with the gravitational wave tidal acceleration. At high frequencies, we're limited by our receiver noise. So this is interferometric noise in the optical metrology system, which is optical interferometry. And this is limited in sort of a fundamental sense by shot noise, so counting statistics of the photons, and by other effects on the optical measurement, which I'll get into at least in part. So LISA, you can see my constellation here illustrated in the top right, has 3 arms, and we exchange light along all 3 arms, which make a nearly rigidly rotating equilateral triangle. It also gives us 3 interferometric combinations, 2 of which are sensitive to gravitational wave, and 1 which you could sort of think of as a Sagnac interferometer, which at least at low frequencies has a very limited sensitivity to gravitational waves. And you could think of as sort of a null channel. So we have 6 one-way laser links going down these arms, which are 2.5 million kilometers. There's some important differences compared to the terrestrial interferometers like LIGO or Virgo. The test masses are truly free falling along the sensitive degrees of freedom. There's no suspension, mechanical or otherwise. They're just free falling. And so this is really an open loop interferometer. The test masses are just following their natural orbits. The sort of Keplerian tidal accelerations, because of their different positions around the sun, the tidal accelerations, the relative accelerations are of order micrometers per second squared, and the gravitational wave signals we intend to resolve are of order femtometers per second squared or even lower. We don't push the test masses to bring them along with the spacecrafts. The spacecrafts are feeling radiation pressure from the sun and the fluctuations in this. The spacecraft are controlled to follow the test masses, and this is called drag-free control. It's an open loop interferometer. We don't sort of lock the fringes, which means that the test masses have a relative motion between them, and that relative motion, just by Keplerian dynamics, corresponds to relative velocities of order 10 meters per second. If you think of the laser wavelength as being around a micron, it means your interferometry fringes are flying by at 10 megahertz type frequencies. It's a very unequal arm interferometer. On the ground, they can make it such that the 2 arms of LIGO or Virgo are the same to much less than a millimeter. And you do this in a Michelson interferometer to cancel out the laser frequency noise. We can't do that if we're letting the test masses fall freely. And over the year, this triangle, this triangular configuration constellation is breathing, and the differences between 2 arm lengths are of order 10,000 kilometers. The last aspect, which has a big influence on what we do, is that it's a very weak light interferometer. We receive light of order a few hundred picowatts. And so you don't just sort of bounce the laser light back and forth using the test masses as mirrors. They are mirrors, but we use what's called sort of a transponder configuration, where we measure the light, measure its phase, and then send it back in phase. We don't have any direct reflection. If we just did direct reflection, you would have less than a photon per second. The other thing is we never, unlike sort of a traditional Michelson interferometer, we never directly combine the light between the different arms. We do this in software, and I'll try to explain this. Okay, this is an ESA-led mission with substantial contributions from NASA and maybe also from Japan. In an ESA mission, the ESA provides the mission prime, the system prime, who has a responsibility for the spacecraft, which are 3 in LISA. They have a responsibility for the launch, the transfer orbit to getting us 60 million kilometers away from the Earth, the propulsion, the spacecraft control, all of the mission operations, some of the science processing on the ground to release data to the public, and they ultimately have responsibility for the mission. I'm showing the spacecraft here. This is just a notional design, which was studied and sort of publicly available by ESA in 2017. Currently, there are 2 competitive mission prime studies going on, which are studying this, and I cannot show images from their studies of what the spacecraft might really look like. This is just a notional concept. Then there is the measurement instrument. And by and large, most of this is going to be contributed by the ESA member states with big contributions from NASA and maybe other international partners. But the main kind of heart of the instrument we call the MOSA. So this is moving optical subassembly. And there are 2 of these per satellite. One pointing down each of the 2 arms, connecting to one vertex of the triangle, which is the spacecraft. And this is comprised of a telescope to send light to the distant spacecraft and receive light from the distant spacecraft. This light is then sent onto an optical bench where the light is combined and interfered against a local laser beam. And then from the optical bench, you go back to the free-falling test mass, which is inside a vacuum chamber. And this setup is called the gravitational reference sensor, which is comprised of the test mass and some hardware around it, which I'll describe in just a moment. We actually measure test mass to test mass in LISA. The spacecraft is not a good enough geodesic reference. We use the test mass, and this measurement of test mass to distance test mass, it turns out, is made up of a test mass to optical bench measurement, an optical bench to distant optical bench measurement, and then a similar pair of measurements at the distant end of this arm. Here you can see some of the countries which are providing these big ticket items, including the avionics that goes with this to actually measure the laser phase and to control the test mass inside its housing. And I think later in the week, you'll have a discussion with ESA and some people from the consortium about hardware opportunities for Canada. So I'll describe first the LISA measurement in some conceptual sense. So in LISA, but also in Virgo, you can think of the basic measurement as a measurement of differential acceleration between free-falling observers, and you measure this differential acceleration in the time-varying Doppler shift. So in my crude way of thinking this, it's a time-delayed Doppler gravity gradiometer. And you could think of the main measurement we do as two observers in free fall. The first one emits a laser beam with a certain frequency, which goes to the second observer. You could think of this as just bouncing back to the first one, reflecting back. Really what happens is we actually measure the phase of the incoming laser beam and create a copy of that and send it back. But you could think of this as light just sort of bouncing back. And then the first observer receives this return beam and it interferes it with a local beam, measuring the differential phase, or we could think of this as measuring what we call the beat frequency, the difference in frequency between the outgoing laser beam and the return beam. And LISA makes this measurement along 3 arms. So if you look at the time variation in this, the derivative of this beat frequency, you can see that this is it's proportional to the gravitational wave strain. So the gravitational wave strain you could think of as being encoded into this beat frequency that we measure. For those of you who are more familiar with the phase shift that you get from gravitational waves, you could just integrate this equation twice on both sides. Written like this, the gravitational wave strain is in direct competition with what we call delta G. So G, you could think of that as the stray acceleration of each observer relative to an inertial frame. If you look at the round trip travel time is 2t, which is 17 seconds in LISA. If you consider times which are long to that, this is really just the differential acceleration of the two free-falling observers. And so the gravitational wave strain is in direct competition with that. It's also in direct competition. If there were no stray accelerations and no gravitational wave, you would just be measuring the difference in frequency of the laser now and 17 seconds ago when the laser beam was actually created. And so you can see how laser frequency noise enters directly into our signal. And then we also have the phase or frequency measurement noise, which you could think of this as being dominated by shot noise, but also the noise in our what we call a phase meter for measuring this beat frequency. So here you sort of see the main noise sources. We typically group the stray acceleration noise into one, and then these two lower terms into what we call optical metrology noise. If you look at our sensitivity, which Kelly described, at low frequencies, and low frequencies for us means below something like 4 or 5 millihertz, we're dominated by the antenna noise. So the acceleration noise for the test masses, the fact that they're not perfectly geodesic in their orbits. And at high frequencies, we're limited by the interferometry noise and the readout noise. As you go to higher frequencies, still this gets higher as you start squeezing more wavelengths of the gravitational wave into the arm of LISA. And the relevant numbers from an experimental standpoint are free-falling test masses, which are free-falling to within a few femtometers per second squared per root hertz, and an interferometry measurement noise, which is of order 10 picometers per root hertz. As I said before, we do this interferometry measurement. What we're interested in is test mass to test mass, but this is actually the sum of three measurements: test mass to spacecraft, spacecraft to distant spacecraft, and then test mass to spacecraft at the far end. And then you could think of this as each spacecraft has two of these setups that you see at the left and at the right, one for each arm. And then we have a third interferometer, which is we call the reference interferometer, which is sort of like the beam splitter in a Michelson interferometer, which it allows you to reference the phase of one arm relative to the other. So I won't go into the beautiful science that Kelly already described, except to say a couple things about the sort of frequency extremes and why we want the performance across the whole band. This is the case of supermassive black hole mergers. This is actually the signal from two 5 million solar mass black holes at a cosmological redshift of 2. And you could look at the signal to noise ratio, which is building up over time and over frequency as this is going to higher frequencies and nearing the final merger. The final merger for this big system is right around a millihertz. So we have no signal at higher frequencies than a millihertz, except for a very quick kind of ring down, which bleeds into the millihertz band. But to see these, we need to observe at frequencies below a millihertz. You could see most of the signal to noise, and this is 1,000, is built up in the last day or even the last hour. So if we were to not do our job at the low frequencies, we would still see these with a relatively high signal to noise, but we'd see them just for hours or maybe a day. These lower frequencies help us to observe this for days to weeks, which gives us more of a hope of doing some of the multi-messenger astronomy. And it also helps us to observe the sky position. Going to sort of the opposite extreme, which you also saw in the last talk, which are these sources, which are kind of solar remnant mergers. These 10 or 15 years before what was observed in the first LIGO detection was observable in the LISA band for some few years at frequencies of sort of the 10 to 20 millihertz range. As they sort of sweep to higher frequencies, our resolution goes down and they spend less and less time. But at the 10 to 20 millihertz, we're definitely limited by the optical interferometry noise. And so we have to get that right also. Also, that's important for some of the higher frequency galactic sources and some of these verification binaries. So the entire frequency range of LISA is important, which means we need to get the free-falling test masses right and the optical interferometry. One thing we talked a lot about years ago, but I think we still talk about this today, is what is really the right size for LISA? Why 2.5 million kilometers? You could see at this current mission that we're designing, you see where the sort of the trade-off is, or the switch, the crossover from acceleration noise dominated to interferometry noise dominated around a few millihertz. The lower frequencies, you're going to more massive black holes. At the higher frequencies, you're going to lighter black holes, and this the possibility of doing sort of multi-band astronomy with LIGO. If you look at what's sort of fundamental, we've always looked at the shot noise, which is really photon counting. If you look at the shot noise, we're not exactly shot noise limited in the current design, but that is a noise source which is definitely there. And we will certainly do no better than the shot noise. We have some hope of maybe doing a little bit better than what we're required to do, but we won't do better than the shot noise, which is limited by how powerful our lasers are and the divergence of the beam. It turns out that this sort of noise minimum, which you see the shot noise limit here, what that level is not really dependent on the arm length. And so, as you go farther and farther away, the beam divergence is making it such that you're getting fewer and fewer photons, but you're gaining back the sensitivity with the same factor because of the arm length and the gravitational gradient growing with arm length. That helps you at all the low frequencies. So as we go to longer arm lengths, you beat the acceleration noise by the same factor. which also means you're doing your work with less and less received light power. So you go to something like 100 picowatts at 5 million kilometers. If you go then to smaller LISA arm lengths, you shift your sensitivity and your first nulls where the round trip travel time coincides with the gravitational wave period. You're shifting those out to higher frequencies, so you do better at the higher frequencies. You lose at the lower frequencies because you have less of a lever arm, let's say. The other thing is at the higher frequencies, to take advantage of the shot noise, your shot noise limit gets even lower because you have more photons, but everything else has to be commensurately improved, let's say. So all the other optical path length errors become relatively more important. And so from an experimental standpoint, something like 2.5 million kilometers means that we have enough power to guarantee that we can do our phase locked phase meter measurement. And it also means that we can build structures which are actually stable enough. We need to resolve 10 picometers per root hertz and not less than 1. So that relaxes a little bit the requirements on how stable everything else needs to be. So this is kind of a happy compromise for the guaranteeing that we can actually do this. What would really help from a shot noise standpoint, what's being looked at for future missions, is have bigger lasers, more powerful lasers, and bigger telescopes, but it's hard to find someone who will actually launch those missions. So for the technology that we have on the table and for the science that we can do and the supermassive black holes and the galactic sources, we're sort of squeezing them all into this window. And so I think this is kind of a happy compromise for LISA, but we could debate this really forever, I think, what is the right size. So as we said, at all the low frequencies, what we're limited by is antenna noise. So how geodesic are our geodesic reference test masses. And this is the hardest thing to demonstrate on the ground because it's hard to do free fall experiments, which have a time scale of tens of minutes to hours. We do some of this on the ground with torsion pendulum small force experiments, but it's hard to reach the same sensitivity we need to really demonstrate that these test masses, which are 2 kilogram cubes of gold platinum, which was the most expensive thing we could find, but it's also the most the densest thing we can find, and it's the most non-magnetic, reliably non-magnetic material we could find. It's it's hard to demonstrate that the stray forces acting on these are smaller than femtonewtons per root hertz. These are 2 kilograms. We need femtometers per second squared. That winds up being force noise limits of order femtonewtons per root hertz. So ESA asked us to do a demonstrator mission where we took an arm of LISA and we shrunk it, oh gosh, down into a single spacecraft with 2 test masses just 40 centimeters apart. And the idea is that most of the noise sources, most of the force noise sources are the same when they will be separated by a few million kilometers. We did this experiment starting at the end of, we launched at the end of 2015. We did this experiment in 2016, 2017. And we did it at the Lagrange point, which is a good place where you can leave the spacecraft with its solar panel looking at the sun, its radio antenna looking at the Earth, and it basically stays fixed or nearly fixed in the Earth-Sun system. So every morning, the spacecraft rises like the sun, and you have a stable setup for solar power and also for communications. So this demonstrated free-falling test masses. It demonstrated the gravitational reference sensor, which I'll explain in just a second for LISA. It demonstrated a local measurement of interferometric measurement of free-falling test masses. It demonstrated spacecraft control at the nanometer level with cold gas microthrusters. It demonstrated some of the other things we need, which are high precision gravitational balancing on board the spacecraft. We had to deal with the test mass charging environment and the space magnetic thermal environments. So LISA Pathfinder, it's a simple freshman physics experiment. You're just measuring the acceleration of 2 test masses. Everything around that is just set up to protect the test masses or to measure the test mass relative motion. So it's, again, two gold, platinum test masses, which are heavy and non-magnetic. It has in the middle, we have an ultra stable optical bench for doing picometer laser interferometry. The test masses are surrounded by an electrostatic shield, which also contains a set of electrodes. Those electrodes are used to measure its position in 6 degrees of freedom, which is used for, if you will, aligning the optical measurement and to controlling the spacecraft. The sort of critical degree of freedom, which is just along the line separating the two test masses, is an interferometric measurement. Those are also an electrostatic shield, and they're also used to apply sort of nanonewton level forces, which are used to align the test masses inside their cages. But the most important thing about this, it turns out, is, and the hardest thing to demonstrate, is that you're actually providing an environment, a Faraday cage, in which you can have femtometer per second squared free fall. There's a vacuum enclosure. It sounds ridiculous because space is a wonderful vacuum, but the spacecraft is quite dirty. It's full of electronics boxes, which are hard to require that they're clean enough. Turns out that we're limited by the Brownian motion of the test masses, and that requires a high vacuum. So there's a vacuum enclosure. There's a caging mechanism, which is just holding the test mass still in the 30 seconds while it's vibrating during launch, and then releasing it once you're in orbit. And then we bring up a UV light discharge system, which is needed to neutralize the test masses from cosmic ray charging. So LISA Pathfinder aimed at doing 3 or 4 orders of magnitude better than what's done for free-falling test masses, which are used. The best ones running are geodesy missions like GRACE, and actually GOCHE is the one which has really demonstrated very high precision free fall. We're trying to do 3 or 4 orders of magnitude jump. Okay, we knew that in going from low Earth orbit to going to the first Lagrange point, you're getting much farther away from the Earth's gravity gradient. And so the forces that we need to hold the test masses inside the same spacecraft are dropping by several orders of magnitude. The actuation noise, which you need to hold the test masses inside the same spacecraft that you have in geodesy missions, is going to be much lower with LISA Pathfinder. What we didn't know, or what was hard to prove, is that the forces, the stray forces acting on the surface of the test mass, are really low enough to make this jump. And to design for this, we used heavier test masses. Most of the dangerous force noise sources are acting on the surface of the test mass. So you gain by going to a very heavy test mass. You gain for a lot of noise sources by using bigger gaps around this test mass, particularly for electrostatic noise sources. We had to cut the wire, which is normally used to discharge test masses, which is a lot easier to discharge a test mass that way. That wire, which was used to discharge a test mass in some experiments, turns out is introducing a lot of mechanical noise. We had to get rid of that. We had to avoid all DC voltages, which couple to the test mass charge and which couple to slowly varying stray voltages. And we use a vent to space, very low pressure vacuum. All of these design changes were costly and make it more complex, more heavy. It makes holding the test mass during launch more difficult. You need a UV discharge system, and you need an interferometer readout. Instead of with very small gaps, you can measure picometers with capacitive sensors. You can't do this with 3 or 4 millimeter gaps. So all of these were costly. And the question in Pathfinder is, do we know enough? Are the surface forces small enough to allow this jump? The answer is yes. I'll jump to that in just a second. I said before, LISA Pathfinder is just a freshman physics experiment of measuring the relative acceleration between free-falling test masses. When we turned on LISA Pathfinder, we could, and you measure this in the interferometry signal and in the feedback signal. So you're applying a force to one test mass to kind of make it move with the other one. And you need this in a single test mass experiment. When we turned it on, we could see how much force we were applying. And you see this here. We were applying forces of around 100 piconewtons, which means 50 picometers per second squared, which was very good news because that absolute number corresponds to how well the local G, the local gravity, was the same between the two test masses, We designed for it to be 0, plus or minus roughly 1 nanometer per second squared. We actually got it right to about 10 times better than that. Turns out that's what was one of our big noise sources. If you look at what we had promised to measure, what our requirements are, were this pink curve. And this turns out to be something like, well, the pink curve was 30 femtometers per second squared at a millihertz. What we thought we could do was this blue curve. This was maybe conservative, but this was limited at high frequencies by what we could demonstrate for our interferometer on the ground, or sort of a worst case estimate of Brownian noise from molecular impacts, and what we thought we'd have for actuation noise. So what we got when we turned it on, basically the first day of science measurements, was this black curve. Over time, what we measured are these red curve, and then this is the first data that we published, and then after a year, we measured this blue curve. And what we're seeing here, it turns out our interferometer is much better. Our first measurements were polluted by the motion of the satellite, which, remember, what we're measuring is differential acceleration between two test masses. To a first order, the spacecraft motion doesn't matter, and it's the same in LISA. To a first order, that subtracts out. When the interferometer is so good, we actually needed to do some kind of calibration to subtract this out. Over time, the environment around the test masses got better as we vented to space and the pressure went down. And because our gravitational balance was so good, we were able to ratchet down the applied forces. And with that, the noise got lower. We were able to make measurements for these and other noise sources to get sort of a real physical model, kind of a laboratory type model of what's limiting the measurement and also what will limit LISA. So I'll try to explain this. This is our LISA specification for differential, for the equivalent differential acceleration of the free falling test masses. The light blue data is what we measured. The dark blue data is what we measured with some properly calculated error bars. This is our noise model, okay? So at high frequencies, at this black curve, this is our noise model. At high frequencies, what we're limited by is the interferometer. At these intermediate frequencies, we're limited by the Brownian motion of 2 kilogram test masses in a fluid of 10 to the minus 11 atmospheres of pressure. And then at low frequencies, what we calculate are that we're dominated by actuation noise and to a lesser degree, some stray electrostatics. So the good news about this is that what we measured is good enough. We don't need to do any better in LISA than what we did in LISA Pathfinder. The bad news is that we're not actually explaining everything that we measured. We're explaining about half of it in linear, or maybe a little bit more than half in linear, which means something like a third actually in noise power. And so we are working furiously to understand this, and we're designing LISA to have the same the same environmental conditions or better, such that if there's something that we didn't fully understand, that we can make this as small as possible and in LISA. Just a few things very quickly. I don't have so much time. We demonstrate a local interferometer measurement. Where we're limited by interferometry noise at high frequencies, the noise floor was 35 femtometers per root hertz, which is almost, well, it's a factor of several hundred better than what we need to do with LISA. We won't do a factor of several hundred better with LISA because we're photon starved. However, we understand how this interferometer works and demonstrate a very high performing interferometer. The Brownian noise, this is just noise due to molecular impacts on the test mass surfaces, is limiting our performance in the millihertz band. We saw this get better over time, and this corresponds, to the behavior of a system, a vacuum system, which is venting and slowly getting better over time. At the end of the mission, this is corresponding to something like a micropascal, so 10 to the minus 8 millibars of water. We actually lowered the temperature in the last part of the mission, and we saw the noise improve even more. And that corresponds, so we lowered the temperature something like 10 degrees, and that corresponds to cutting the outgassing for water by something like a factor 2, and we saw the corresponding noise improvement. So we're fairly convinced that's what we're seeing, and this is certainly good enough for LISA. This was actually better than what we need for LISA. I won't go into the details of this, but in LISA, we need good gravitational balancing. We have this is very simple on paper. It's just 1 over r squared, summing all the mass on board, but realizing a spacecraft which is balanced at better than, so at something like the 10 to 100 pico-G level is very difficult experimentally. We think we have this under control. We demonstrated what we need to do for LISA. We also demonstrated very stable sort of nanonewton level actuators. We don't need these on LISA for controlling the translation of the test mass. We do need to use them to line up the test mass, to align the test mass to our optical measurement. And we have a good handle on this noise, which we were able to measure by sort of exaggerating, applying big forces to the test masses and seeing how our overall noise deteriorated. We measured the test mass charging, and we resolved both the sort of deterministic just charging. We also resolved the charge noise, so the Poissonian nature of the cosmic ray charging. And this is also an important step for LISA. We demonstrated that you can control the spacecraft to sort of nanometer per root hertz type precision. We need this for LISA as well. And this has been demonstrated. So I've maybe given the idea that we've done everything. We certainly have not. I'll try to use these last few minutes just to kind of explain what's still left to be done for LISA. I'll be shortchanging some of this just because of time. But so what's left to prove? And the answer is really the long arm interferometry. So exchanging photons between the two distant spacecrafts. This is the acceleration signal from a supermassive black hole. This is the differential acceleration signal from the supermassive black hole in green. Once you've superimposed the acceleration noise that we measured in LISA. So as I said before, LISA is good enough as an acceleration noise LISA Pathfinder is good enough from a demonstration of a test mass acceleration noise to do LISA. You will see this signal by eye without any real special analysis. You'll see this signal in our data stream from an acceleration noise standpoint. Here we're sort of zooming in and you could see maybe that there is some wobble to this at low frequencies. This is the last day of the supermassive black hole merger for 500,000 solar masses. But this is slightly unfair for one reason, because I'm not using, in LISA, we will be photon starved, whereas in LISA Pathfinder, we could use a milliwatt of light. In LISA, we'll have 100 picowatts or a few hundred picowatts. If I add that in, our signal starts to look like this. Additionally, as Kelly said, we'll have a confusion noise limit from all the galactic binaries, which will add some effective noise, which looks like this, the pink data. If I consider just the raw laser frequency noise, if we did a simple Michelson light combination, you would have this black noise, which is completely overwhelming everything. And you'd have to zoom out, and our supermassive black hole is this red signal, and our laser frequency noise is this black noise here. That's because the arm lengths in LISA are different by up to 10,000 kilometers during the year. And I'll just explain briefly the complications of this. So the beam divergence over a few million kilometers is such that the beams at the distant spacecraft are of order tens of kilometers, and you're just resolving, you're actually receiving light from a 30 centimeter telescope, and that knocks the amount of photons that you're receiving. It's about 1 for every 10 to the 10. And you have just a few hundred picowatts of power. The other aspect is that the LISA constellation is almost, just by the magic of Keplerian dynamics, it's almost a rigidly rotating triangle configuration, but it has what we call a breathing, which means that the angles are not exactly 60 degrees. They change by something like plus or minus 1 degree over the year. The arm lengths are not exactly the same. They're up to tens of thousands of kilometers different. And the same dynamics gives you this relative motion of the Doppler shifts, which are of order 10 meters per second. which corresponds to 10 megahertz Doppler shifts in the light. So LISA is
Bill,
weak light, it's open loop, and it's an unequal arm interferometer.
Bill, sorry to interrupt, but I just want to give you a heads up. We've got about 5 minutes left in this session.
Okay, gosh, I have maybe 2 minutes left,
Great.
and then we can hopefully have a minute left for questions.
Sounds great.
So,
Thanks.
I won't go into the details, but if you were to just combine the light like you do in a laser Michelson interferometer, and I lump in the laser noise with our sort of fundamental phase meter noise dominated by shot noise, what you find is that in a simple Michelson interferometer, the fact that the arms are not equal couples into our signal, giving you something like micrometers of noise, and we need picometers. So instead of arms that are 20,000 kilometers different, we need arms which are the same to within just a few meters. And we can't do this with the Keplerian dynamics of the constellation. However, what we do is we synthesize offline in software, we synthesize with a technique known as time delay interferometry, which you'll see, I think, in a couple of days in the data analysis portion of your workshop. You'll see time delay interferometry, where we resample these phase measurements. We resample them at precise times, where precise means to within nanoseconds, so within sort of meters of precision, knowing the arm lengths or doing ranging to get the arm lengths to within meters. We can resample the data in such a way to cancel out the laser frequency noise. And if you want to think of this conceptually, you're sort of comparing optical paths which travel down one arm and back, and then down the other arm and back with light which travels the same path, but in the opposite direction. And if you do the math on this, you find that you're sort of high pass filtering most of your noise sources, and you're high pass filtering the gravitational wave, but you can do this in such a way that the photons that you're comparing were emitted basically at the same time. And in this way, you can cancel out the laser frequency noise, and you can do this to high precision. It turns out you need to do a sort of a second order, where you actually do, instead of 4 light pulses, you do 8. This is called TDI 2.0, and this is taking account for the fact that the arms are not just different, they're actually changing in time. We call this flexing, and they're also rotating. So you could do this in such a way as to synthesize an equal arm interferometer, which has a sensitivity similar to a Michelson interferometer, but you've killed the laser noise. And this is rather impressive, because in the end, I won't go through all of this, but you're removing something like 6 orders of magnitude of laser frequency noise. This puts a high burden on your dynamic range of your phase meter, where you've got 10 megahertz sort of deterministic orbital Doppler shifts. You have laser noise of 30 hertz. And what you're trying to resolve are modulations of the laser frequency by the gravitational wave, which are of order a microhertz or even less. This has been demonstrated on a benchtop with the phase meter that we have, but we need to do this in flight. Some of the interferometry challenges have been met also with recent geodesy experiments or laser ranging experiment on the GRACE mission, which I won't go into. You're also, I'll just say this very briefly, you want to do picometer measurements, and your spacecraft is moving by nanometers, which means you have a high dynamic range subtraction in combining the local interferometer between test mass and spacecraft, and the distant interferometer, which is spacecraft to spacecraft. So you have to do this. You also have a problem that your spacecraft is going to be rotating, and there's a conversion, we call this tilt to length coupling, where this rotating spacecraft gives you a longitudinal and effective translational error. And it turns out that we're going to have to do likely some subtraction on this. You could think of this as coming from our alignment problems between this long interferometer and the test mass to spacecraft interferometer. It's likely that some of our initial data processing will have to subtract this, that we won't get this all right in hardware. Finally, the last thing I say is that we also have some sort of engineering details, I guess, from an experimental physics standpoint. One is that you actually have to survive launch. So you have to hold the test masses during the 30 seconds where the spacecraft is vibrating violently, which is sort of like parking your car with one wheel on top of the test mass. And then once you're into orbit, you want to release these very gently with a very low velocity such that we can catch it with our electrostatic suspension. In LISA Pathfinder, we didn't get this right until sort of the end of the mission. The test mass bounced around. So this is one of those sort of little engineering details that we have to get right. I think we're on a good path for this. The other thing is that you're in deep space and you actually have to find the distant spacecraft. You know where it is just from ground tracking to within a few hundred microradians of angle. That's its sky position. And you have a pencil laser beam, which is a few microradians wide, with which you have to shoot out at the right angle such that you find the distant spacecraft. And this is a rather complex dynamics problem. And you also need to sort of scan both the angles and the laser beam frequency to find these on your detector. So these are just little engineering details, but we have to get these right. This is just to give you some of the idea of what we're trying to do. I won't go into this. There's a unique instrumentalist challenge, which is that your instrument noise will be superimposed with your signals in LISA, which is a little bit different from at least the current LIGO, where you have 1 second of signal for every million seconds of data. Kelly's signals are turned on all the time, and there's tens of thousands of them. So this is a challenge also then to tell you, well, how well is the instrument working? So this is part of the exciting experimental challenge. I think I was a little bit long and I apologize for that. But anyhow, thank you for your attention and thanks to the consortium. I'm hoping that we'll get to meet in person at some point. So
awesome. Thank you so much, Bill. If people are comfortable turning their videos on and joining me in clapping, it's always nicer to see faces than just emoji hands. So